Hi, everyone. Thanks for coming to the Earth System Grid Federation webinar series. We're just trying to launch this webinar series and hoping that users and developers and folks that work with Earth System model output will be interested in joining us. We're going to cover a variety of things, including tools and methods and applications. And for this first webinar in 23, we're fortunate to have Tom Vo from Lawrence Livermore National Laboratory give us a talk about a tool that he's working on developing called xCDAT. So take it away, Tom.
Thanks, Forrest. Thank you for this opportunity. I'm very happy to be able to present xCDAT for you all, and hopefully you get some value or interest in this tool. So the presentation is called a gentle introduction to xCDAT. So it's Xarray climate data analysis tools. The little slogan is like a Python package for simple and robust climate data analysis. So I'm one of the core developers. We also have folks from other projects, including PCMDI and EVSM and the SEEDS project. They include Stephen Pochedli, Jason Butte, Jill Zhang, and Jiwoo Lee. We also have Peter Gleckler, Paul Durack, Carl Taylor, and Chris Golas, who provided a great insightful knowledge in helping us get moving in this project. So just a little quick overview of this presentation. It's kind of intended for those who aren't that familiar with Xarray or xCDAT. So, if you have a lot of knowledge, it might still be helpful just to understand the background of xCDAT at least. So I'll be talking about essentially the driving force behind xCDAT, what actually got it kicked off in the beginning, some of the goals and milestones of CDAT's successor, which is xCDAT. I'm gonna give a little introduction of xCDAT, just the basic knowledge on how the project is funded. And then before we jump into the internals of xCDAT, I want to do a little briefing on Xarray, some of the basics, like the data models, and then talk about how xCDAT extends Xarray, the technical design philosophies, the APIs, some demos of those APIs, and then how to get involved in the project. So the driving force behind xCDAT, essentially it revolves around the Community Data Analysis Tools library. It's a suite of robust and comprehensive open source tools for climate data analysis and visualization. It's been in the open source community for over 20 years. ESGF was one of the primary funding sources for the past, like probably 10 years or so. I'm not too sure, but they were definitely, leveraging CDAT. So essentially, as time goes on, software evolves, data grows. There's just a driving need for modern tooling, and what xCDAT focuses on is a maintainable and extensible library that serves the needs of the climate community in the long term. So some of the goals and milestones for xCDAT include offering similar core capabilities of CDAT, including geospatial averaging, temporal averaging, and regridding. We also want to focus on modern technologies in the library stack. So things such as supporting parallelism and lazy operations. As data size grow, you want to be able to operate them efficiently. So these are things that we definitely keep in mind. We want to make sure it's maintainable, extensible, and easy to use. So following software engineering standards and best practices, including the Python enhancement proposals, automating DevOps processes, and making sure the documentation is up to date. A big key point is number 4. So we definitely want to cultivate an open source community that can sustain the project for years to come. So we are encouraging a lot of GitHub contributions, discussions. I'll go over that at the end of this talk. And then community engagement efforts. So participating in Pangeo discussions, presenting in the seminars. And obviously here in ESGF, we want to become a part of the community and hopefully have xCDAT fit some kind of a use case here. So introducing xCDAT, it's an extension of Xarray for climate data analysis on structured grids. We want to provide simple and robust analysis tooling for climate data. As I mentioned before, it's jointly developed by scientists and developers from several projects, including EVSM, PCMDI, the SEEDS project. And as the project is growing, a lot of users are starting to participate through GitHub, which is awesome. I'm seeing more traffic and more discussions going on from other organizations and so forth. So that's very awesome news. So before we dive into xCDAT and get into the internals, I want to talk about Xarray, since that's the foundation of xCDAT. For those of you who aren't familiar with Xarray, it's an evolution of an internal tool developed at the Climate Corporation. It was released in open source in May of 2014 and has been fiscally sponsored since August 2018 by NumFocus. NumFocus is an organization that sponsors a lot of projects that are open source for better science, such as NumPy, Pandas, and so on. So you would know that since Xarray has its backing, it's definitely going to be a part of the community for a while, and it's going to be sustained and pretty robust. Some key features and capabilities in Xarray. So their motto is pretty much ND labeled arrays and data sets in Python. It's built on and extends NumPy and Pandas, and has interoperability with the scientific Python ecosystem, including NumPy, Dask, Pandas, and Matplotlib. Some of the cool features include file IO, grouping, parallelism, as I mentioned. That's something we focus on, so Xarray has that capability. And then plotting, so it just has a simple Matplotlib wrapper if you want to do some quick plots. And the file formats include, the support file formats, netcdf, iris, OpenDAP. So it has a ton of supported formats that you could utilize with Xarray. So why would you want to choose Xarray? Xarray introduces this concept of labels in the form of dimensions, coordinates, and attributes. And they place that on top of these raw NumPy arrays that you might be used to working with. And in doing so, it allows for a more intuitive and concise experience that developers, they would have less error-prone code, and that makes it much more efficient experience overall. So I won't go through these like in depth, but these are some of the ways that you can apply these labels when you're working with Xarray objects. So for example, you want to apply operations over dimensions by name. You can do a sum on that object and then do a time. That's the label. Very easy. Rather than trying to find which axes and which, those arbitrary numbers, those are very hard to map to dimensions. So you're just calling it by this label here. Group by. So you want to do a group by on the time of the day for the year. So time, day of year, that's just a label. You're doing group by and you're calling a mean on that. So you just kind of see how it's similar to Pandas if you ever use Pandas. And I personally like this way of working with this data because it's very explicit and easy to follow. If you're interested, I have a source down here that you could follow for more information on this. So the Xarray data models, they're borrowed directly from netcdf. It provides Xarray with a natural and portable serialization format. There are two data models that we're focused on, the data set and the data array. The data set is just a container of data array objects with aligned dimensions. And the data arrays are classified as coordinate variables or data variables. They have a shared union of coordinates. And if you notice the structure, it's pretty similar to a data frame in Pandas. As far as the data array, it's just a class that has dimension names, coordinates, attributes on top of those multi-dimensional arrays. And it's similar to a Pandas series. So if you look on the right, there's an image from the Xarray website that kind of lays out how these models work together. So at the very bottom, you have a data set, and then it encompasses all of these data arrays here. So we have the data variables, temperature and precipitation. We have the coordinate variables, which are latitude and longitude. And then we have the aligned dimensions for these variables. So we have X, Y, T, and then they're just showing a reference time here. So now we're actually going to open up a data model, the data set, and this is actually straight from ESGF. We're using Xarray's OpenDAP support. And for this specific data set, we're opening up a TOS variable, so near surface air temperature, and it's recorded on a monthly frequency. We want to go back 1 second. So I do want to mention that no data is actually downloaded until you're doing computations. So that's a really cool feature of Xarray. When you're loading up a data set, let's say from ESGF's OpenDAP support, it's just going to show the representation of it, but it won't actually do any loading of data into memory, which saves you some space and potentially download time. So this is the data set that I just opened. You can see it's a container of labeled arrays. We have the dimensions up here, time, bounds, lat, lon, and then we have coordinates. These are those coordinate variables I mentioned, time, lat, lon, and then it's aligned to these dimensions up here. And then we have the data variables. So this is actually the variables you want to work with: sea surface air temperature, TOS, and it uses the time, lat, lon dimensions. And then we have a bunch of bounds variables, so they align to whatever coordinates those bounds belong to. Attributes, let's see. So attributes, this is just a dictionary, so pretty simple. Just holds all the information that is related to this data set. So now we're diving a layer deeper, the data array model. It's a class that touches dimension names, coordinates, and attributes to those arrays. So you can see we have the values here. They're pretty large, so they're not going to show. There's over, I think, 55 million or 5 million. They're float 32. And then the coordinates I mentioned, and attributes, and then dimensions at the top here. So I think it's pretty straightforward overall to work with and look at these data models. So kind of set the stage for Xarray, built the foundation, and then we can move on to xCDAT. But if you're not too familiar with Xarray or haven't really worked with it, I provided some resources from their official documentation, and I highly recommended them. They're really easy to use and follow, so give that a shot. So now that we understand kind of the Xarray base of xCDAT, I want to jump back into xCDAT. I mentioned before, xCDAT has features from CDAT that we wanted to port over. So that includes, spatial averaging, temporal averaging, and then the regrid2 API for horizontal regridding. We also leverage powerful libraries in the Xarray ecosystem. So we have XCSMF, XGCM for regridding horizontally and vertically. And then we utilize the CF Xarray package for CF convention metadata interpretation. We also strive to support data sets that are CF compliant. And also there are some cases where there are very common non-CF compliant metadata. So specifically the time units in months since or years since, we have some logic that parses those and decodes the time coordinates. And we'll try to consider some other cases as they come up, but these are the most common ones that we ran into so far. We also have, I mentioned how Xarray has the support for Dask out of the box. So xCDAT inherently, since it's based on Xarray, has support for lazy operations and parallelism using the Dask support. So the technical design philosophy of xCDAT is kind of just focus on streamlining the user experience of developing code. So that means, there are certain features in Xarray that the user might need to implement on their own since they're not provided out of the box. Xarray tries to avoid being too domain specific, so they don't provide temporal averaging or spatial averaging specifically for climate data analysis. And that's where xCDAT comes in. We really want to focus on reducing the complexity and overhead of these features, and users basically encourages users to work together in a single implementation that is shared and reused. And that way we are focused on building like a really robust tool set for the community. Oftentimes people develop their own unique temporal averaging and there's like 20 implementations on GitHub. And it's difficult to figure out which one to use. So having just like a single source of truth that people could contribute to is definitely one of the big goals here. So we have two ways of leveraging the APIs of xCDAT right now. So we have the top level APIs, similar to how Xarray does it. So we have the open data set and the center times functions. Usually these top level APIs are for opening data sets and also performing data set level operations. We also provide the accessor classes. So this is just a way for us to extend Xarray objects with their own implicit namespaces. The accessor classes identify the custom functionality of xCDAT and makes it so that it's obvious that these functions are from xCDAT rather than from built-in Xarray methods. So you can see how we have this dataset object here. We have the accessor class in the middle. So we have the spatial accessor, and then we have the .average method. So once you chain this spatial accessor, you have access to all of these methods and attributes of the spatial class. So here are some of the key features. I've already mentioned a few of them before, the temporal averaging and so on and so forth, regrading. As far as the description, so some of the cool things about the open dataset and OpenMF dataset extensions is that we have bounds generation. So Xarray doesn't have this. When you're opening up a dataset, sometimes it's missing bounds, and you need those to operate on and use for calculations. So we automatically generate them if you specify a flag. We have flags for other operations and processing here. So, and then as far as temporal averaging, just the usual things like climatology, departures, and then group averaging. And then for horizontal regrading and vertical regrading, I mentioned that we extend XESMF and XGCM. So for those extensions, we generate the grid object, we create an output data set, and then we also preserve and generate bounds that are missing. So now I'm going to actually demo some of these features, how you can get started with the prereqs. So installing xCDAT and then importing and opening data sets. And then I'll do some demos of some scenarios that climate scientists might run into. So spatial averages over tropical region, annual anomalies, and horizontal grading, bilinear and Gaussian grid. So I'm just opening up the same data set that I did before. In this case, I'm going to specify some flags. So I'm going to make sure to add bounds that are missing. Make sure to decode the times to perform our xCDAT temporal operations, and then center times using those bounds. So all these are true. And then we're going to do some unit adjustment here, just convert from Kelvin to Celsius using this formula. So this is just what the data set looks like. It's pretty much the same as that earlier slide. So we're basically just performing a spatial averaging over tasks and then plotting the first 100 time steps. So you can see the spatial average method that I mentioned earlier. We're passing the task variable. That's the variable we specifically want to work on. The axis where we want to average over, and then the lat bounds, which represents the region. So this is the tropical region. And then I'm just printing out the object here. So you can see how we've collapsed the X, Y axes. They've been averaged over, and now we just have the time dimension. And these are the average values over those coordinate points. Here's just a simple demonstration of the Xarray wrapper of matplotlib. I'm doing a dot plot, and I'm doing a iSlice. So we're selecting an index of the time. So I'm using that label I mentioned. And then we're doing a slice of 1 to 100. So the first 100 time steps. And this is kind of what you get here. Next, we're doing calculating a temporal average of tasks as a single snapshot. So in this case, we're just doing an average of the entire time coordinates and collapsing the time dimension. You can see I'm calling the temporal accessor, doing an average, passing the variable name, and making sure it's weighted. So we set true here. You see how the time dimension is now collapsed. We just have lat lon and the average values for those coordinate points. And then this is what it looks like when you're doing a quad mesh, and then doing a label is weighted. So also a cool thing is that we do add attributes after you perform these operations. If you notice on the bottom left, we add the operation you perform is temporal averaging, the mode is average, and then those options that you selected. So weighted is equal to true. The frequency is inferred. So, when it's loaded into xCDAT and you call this average method, it will look at the bounds and then infer the frequency from that. Next, we're doing a horizontal gridding. So generating a Gaussian grid with 32 lats to regrid our input data to. First step, we're going to create the output grid. We provide several APIs to create grids. So this is the Gaussian grid API. We're passing 32 lat points, and then this is the output grid data set. We're now going to plot the input and output grid just to compare what they look like. So this is the input data's grid, and then the output grid that we want to regrid to. So now we're actually going to use the regridding accessor and the horizontal method. So that's a horizontal gridding method. We offer two horizontal gridding tools. So we have the xESMF extension, and then the xCDAT regrid 2 Python port. So that's coded directly in Python. Jason was the one that did most of the work here. So as you can see here, we're doing regridder accessor chain, and then horizontal method, passing that toss variable. And then the output grid that we created earlier, we're going to pass it here. Specify the tool, xESMF, and then the method, so bilinear. xESMF does support conservative, and then all nearest STD, and then DS2, D2S, and patch. As far as plotting, you can see the input data and then the output data. So we're just plotting what it looks like before and after. So we have the input data grid here, and then after we pass the output grid, you can just see how it definitely changes the quad mesh. So that's just a demonstration of pretty much how you leverage those APIs and how straightforward it is to chain those accessor methods and then calling those functions. Now I want to talk about how you could work with Dask and using xCDAT. So basically all the Xarray methods have been extended to work automatically with Dask arrays for parallelism. So things like indexing, computation, concatenating, group operations, those all have pretty much been extended to work with Dask. And I mentioned how xCDAT is built on Xarray. So as long as we're leveraging those Xarray methods, we have inherent support for Dask. And the Dask arrays are only loaded into memory when absolutely required. So in xCDAT's case, that includes decoding time and handling bounds. So we need to actually load those Dask arrays into memory in order to do some computations and then parse them for like decoding, for example. So some high-level overview of Dask mechanics. This is just, if you're not familiar with Dask, just a little like summary of how it kind of works under the hood. So those Dask arrays, they're divided into small pieces called chunks that presumably fit into memory. And the operations performed on those arrays are lazy. They queue up in a series of tasks mapped over blocks, and no computation is performed until the values need to be computed. So that's where the lazy portion comes in. Data is loaded in memory when computation is needed, and then it's in a streaming fashion, block by block. The computation is controlled by multiprocessing or a thread pool, which is, you could control that or allow Xarray to determine which is suited for your machine. So how does Dask actually work with Xarray and xCDAT? So the usual way is to create a data set filled with Dask arrays by loading it from netcdf. You supply a chunks argument to the open dataset or open MF dataset functions. By default, the open MF dataset does already chunk, but it only does a single Dask array. So it's not actually chunking or doing anything in parallel unless you specify. That's just the default behavior. So as I mentioned, you pass the chunks argument to control the size of the Dask arrays, and then Xarray maintains Dask arrays until it's not possible. So it won't load into memory unless you explicitly tell it to. xCDAT does in some cases, like I said in the other slide, we do have to load it into memory for decoding time, but Xarray won't do these things implicitly. So I'm opening up the same data set as the other examples, and I'm passing the chunks argument here. So time, we're chunking on time. I'm setting it auto just because I want Xarray to handle how many chunks it thinks is appropriate, but this definitely varies by data set size or your machine. You could pass in like 5, 10, whatever you think is optimal for chunking. I will provide more information like how to specify chunking sizes on another slide. So, it definitely varies by machine. So this is a data set that's been chunked. You could see the data variables down here. They're now Dask arrays instead of NumPy arrays. It's kind of hard to see, but hopefully you could see how there's a chunk in an array columns, and then you can see the shape, how many the Dask graph, how many chunks in the 3-graph layer, and then the underlying the data type. So it's an MD array at the base level. So this is just what Xarray determined with its auto chunking. Yeah, so same thing here. Actually, I don't think Xarray chunked the lat bounds and lot bounds because it's not on the time dimension. It chunked the toss and time bounds because they're using the time. And you can see how there are bytes here. So this is around 130 megabytes per chunk. We're going to apply the parallelism using xCDAT spatial averager. So just demonstrating how you could leverage Dask and then just call some of the xCDAT methods. I do want to note that the generation of weights is serial because we need to load into memory the time bounds, or the time. I think it's the lat bounds actually, yeah. And then to generate the weights, and then we do a parallelized operation on using .weighted API, and then so basically we intend on doing more performance metrics. We need to still figure out like some guidance on when to use chunking. We have an open discussion here for best practices. So that's still in progress, but this is just an early demonstration on how you could get started with parallelism. So it pretty much looks the same as if you're running a serial operation. It's just operating on the pre-chunked data set now. You can see we're calling the same spatial averager, passing toss, same options here, and then we're extracting the toss variable. You can see the output, it's now chunked rather than showing all the values in one array. It's 9 kilobytes per chunk. Shape here is 1205. That's just how it seems like Xarray determined the shape for chunking. So yeah, this is pretty much how it looks like if you were to run it afterwards. Further Dask guidance. So these are some links if you want to try to dive more into Xarray with Dask. Like I mentioned, we're going to provide some more guidance specifically for xCDAT, but that's currently in progress. So some key takeaways from this presentation. I mentioned, there's a driving need for a model successor to CDAT. We want to serve the climate community in the long term. xCDAT is an extension of Xarray for climate data analysis on structured grids. And our goal is to provide features and utilities for simple and robust analysis of climate data. Lastly, just some ways to get involved with this project. So it's mainly through GitHub. We really appreciate and welcome code contributions. Some links here for the repository and the contributing guide. We also really support, users doing submitting and addressing tickets, whether it be for features, bugs, so on. Any help is really appreciated. and then participating in forum discussions. So just getting involved in the community, talking about, some suggestions, anything that is related to xCDAT, and then we really want to make this project a community project. So getting involved is definitely the first step. With that being said, I'll take questions. Appreciate it.